Friends, welcome to the tutorial series on network analysis made simple. This is a module-wise electric circuit analysis paper solution series. In this tutorial, we are going to solve VTU CBCS scheme electrical circuit analysis paper of December 2017, January 2018, module 2 of syllabus 15E32. Friends, I prefer to emphasize on basic concepts, strategy and thinking process rather than detailed mathematical steps. I am sure you already have well equipped with relevant mathematical skills. Hope this tutorial ignites some of your thoughts. Let's go ahead. Friends, first let us answer question 1. In this question, we are required to state and explain maximum power transfer theorem for DC circuit. Friends, we know that in electric circuit, the load receives electrical energy via supply sources. Power transfer in electric circuit is a continuous process. Power is transferred from one circuit to another or from one circuit to load. But from any source of power, how much power is transferred and what is the transfer efficiency, this aspect is the concern of the circuit designers. A logical question arises in our mind, such as, can we design the circuit to transfer maximum power across the load, and what could be the load impedance that it has to have for maximum power transfer? To find out that, consider a DC circuit source voltage Vs and source internal resistance Rs and varying resistance load as shown in figure. The strategy will be find the equation for IL, find the equation for power P transferred to the load. Differentiate the equation of power with respect to RL and equate it to 0. Obtain the condition for maximum power transferred to load. Find the equation for the maximum power transferred. We know that current IL is equal to Vs divided by Rs plus RL, and power across the load P is equal to IL squared into RL. By substituting for IL and solving, we get P is equal to Vs squared into RL divided by Rs plus RL whole square. By differentiating the equation for power with respect to RL and equating dP by dRL equal to 0, we get the condition RL is equal to Rs. By substituting the value of RL in place of Rs and solving, we get Pmax is equal to Vs squared divided by 4 times RL. Hope you understood it. Friends, next we shall solve question 2. In this question, we are required to find Thevenin's and Norton's equivalent circuit for the network shown in figure. The strategy will be, using suitable circuit solving technique, find the open circuit voltage VOC. Note, VOC is equal to VAB is equal to VThevenin. To find VOC, by writing the Kirchhoff's voltage equation for the input loop, we get 2 times VAB plus 805I minus 12 is equal to 0. By rearranging it, we get equation 1. Observe the output circuit. VAB appears across 40 ohm. By writing the Kirchhoff's nodal equation for the output circuit, we get VAB divided by 40 plus 10 times I is equal to 0. By rearranging and solving, we get equation 2. By solving the two simultaneous equation 1 and equation 2, we get VAB is equal to minus 960 volts. Hence, VThevenin is equal to minus 960 volts. Friends, next to find ISC, by short circuiting the terminals A and B, we get to the circuit shown in figure. By shorting A and B, VAB becomes 0. Note that. Further, 40 ohm is short circuited, hence it can be removed. By writing the loop equation for the input loop, we have obtained equation 1 already, but VAB is equal to 0. So, we get I is equal to 12 divided by 805 amperes. But observe that ISC is equal to minus 10I. By substituting for I and solving, we get ISC is equal to minus 0.149 amperes. Hence, IN is equal to 0.149 amperes. We know VThevenin or VOC is equal to minus 960 volts. Therefore, RThevenin is equal to VOC upon ISC. By substituting the values, we get RThevenin is equal to 6.442 kilo ohm. We know RThevenin is equal to Rn. Knowing VThevenin, RThevenin, IN, the Thevenin's and Norton's equivalent circuit drawn are shown in figure. It's very simple, isn't it, friends? Friends, next we shall answer question 3. In this question, we are required to state and prove reciprocity theorem. Friends, reciprocity is a property of an electric network. It states that in a linear, bilateral and single source network, the ratio of source and response remains the same even after interchanging their positions. To apply reciprocity theorem, the network should have single source. It should contain passive linear network elements and the initial conditions are assumed to be absent. Dependent sources are excluded. Friends, to prove reciprocity theorem, consider a simple single source network shown in figure. Observe the network. The resistance R1 is in one branch and R2 and Rx in series is in parallel across R1 as shown. There is a single current source of I amperes. The response is Vx. Using parallel branch or current division theorem, we have Ix is equal to impedance of the other branch divided by sum of the two parallel branch impedances into the total current I. But the response of Vx is equal to Ix into Rx. By substituting for Ix, we get Vx is equal to R1 into Rx divided by R1 plus R2 plus Rx into I. Friends, next, by interchanging the positions of the source and the response, we get the circuit shown in figure. Note, the source of current I amperes is introduced where the response was Vx, and also note the direction of the current source introduced is such that it will drive the current in Rx in the same direction as that in the original network. Now, the response is the voltage Vy across R1. This is the place where the source was present in the original network. Note that. Observe the network. Now, R1 and R2 are in series in one branch and Rx is in parallel across that branch. Using the parallel branch theorem, we get Iy is equal to Rx divided by R1 plus R2 plus Rx into I. But the response Vy is equal to Iy into R1. By substituting for Iy, we get Vy is equal to R1 into Rx divided by R1 plus R2 plus Rx into I. We already found out Vx. We find that Vx is equal to Vy. Hence, the reciprocity theorem is proved. Hope you understood it. Friends, finally we shall solve question 4. In this question, we are required to find current I using superposition theorem. we know that we need to consider only one source at a time, during which time the other sources are to be forced to zero. The total response will be the algebraic sum of all the source responses. Now, observe the given network. It has one independent current source of 2 amperes and an independent voltage source of 4 volts. Note, it also has voltage controlled voltage source of 3 VR volts. But remember, we need to find the response considering only independent sources one at a time. Now, considering only a voltage source, the current source is to be forced to zero by opening it as shown. We find that the circuit now contains only one closed loop. Let I1 be the current due to only voltage source. By writing the Kirchhoff's voltage equation for the closed loop, we get 3VR minus 5I1 minus 4 minus 2I1 is equal to 0, but VR is equal to 2 times I1. By substituting for VR and solving, we get I1 is equal to minus 4 amperes. Friends, considering only a current source, the voltage source is to be forced to zero by short circuiting it as shown in figure. Now, the circuit reduces to a single unknown node voltage V1. Let I2 be the current due to only current source. By writing the nodal equation for node V1, we get V1 by 2 plus V1 minus 3 times VR divided by 5 plus 2 is equal to 0. By solving it, we get 5V1 plus 2V1 minus 6VR plus 20 is equal to 0. But VR is equal to 2 into V1 by 2 and that is equal to V1. Hence, by substituting for VR and solving, we get V1 is equal to minus 20 volts. But we know I2 is equal to minus V1 minus 3V1 divided by 5 and hence we get I2 is equal to minus 8 amperes. But current due to both the sources I is equal to I1 plus I2. By substituting for I1 and I2, we get I is equal to minus 12 amperes. Friends, for strengthening your basic concepts and developing your thinking process, I suggest you refer my textbooks, Network Analysis Made Simple, Basic Electrical Engineering, Basic Electronics, and Linear Integrated Circuits and Applications, which are available online. Thank you for watching this video.